G'day guys, welcome back. This is our final video where I attempt to prove for you the work energy formula for particles. So for the last time, let me bring up again our particle of mass m, and it's swooping out some complicated path just here because we said there were only three forces on this thing. We said there was a force F1, which we assumed was our force due to gravity. There was a force F2, which we assumed was from a spring, and there was this mysterious third force, which I'm about to talk about just here, F3, right? And in case you don't remember, what we managed to prove by the end of the last video was the change in kinetic energy plus the change in gravitational potential energy, plus the change in elastic energy is equal to your work done by this third force between positions 1 and positions 2. Now, if you're just watching part 4 and you haven't seen parts 1, 2, and 3 yet, that's okay. I'll just quickly expand out these terms so you're not completely left in the dark. Delta KE was, and we showed it was in the first video, a half times by m v2 squared minus v1 squared, where v2 was the speed of your particle at its second position, v2, and v1 was the speed of your particle at its first position. And we're completely free to define where we chose our first and second positions. Okay? Now, delta GPE, your change in gravitational potential energy, was mg y2 minus y1, where g is your acceleration due to gravity, 9.81 for Earth in meters per second squared, and y2 and y1 are the heights of your particle at positions 1 and positions 2. So this right here would be y1, and this right here would be y2, right? And they're from any arbitrary axis, right? This is our axis, and it doesn't matter where we place the axis, y1 and y2 will be defined as such, okay? Now, delta EE, your change in elastic energy, is a half times by K times by L2 squared minus L1 squared, where K is your spring stiffness of your spring, and L1 and L2 are the amounts your spring has been stretched at positions 1 and positions 2, okay? Now, W3 is just the work done by this mysterious force between your positions 1 and 2, okay? Now, it's worth mentioning that this formula only applies in the case that there's specifically 3 forces on this particle, right? I simplified this problem to a simple case where there's only 3 forces. But rest assured, it can be generalized further. And let me write it out. Let's say, in general, so we'll write down in general, your work done by your third force will become the work done by all other external forces on your particle. So to make that abundantly clear, like we could have thousands of forces on this thing, but in order to generalize it, we're going to say that F3 is going to be all other forces. So it's going to include force 4, it's going to include force 5, it's going to include force 6 and force 7, etc., etc., and etc. And if we do that, then we get this. And let me copy and paste it. There we go, I copied and pasted it. We get the exact same formula, except we're going to get rid of this subscript 3 here because W3 is now the work done by all other forces in the general case, right? So let me box this off just here. Let me box this off just to signify its importance. And this is something you should write down. This is the very general expression just here, right? Let me star it on both sides like this just to show you how important it is. So to summarize, if there were like maybe 5 other forces, maybe a friction force, maybe a few normal forces, maybe someone's pulling on the thing, then you'll have to find out the work done by all of those and account for them, okay? However, just because there might be other forces acting on your particle between positions 1 and positions 2 doesn't necessarily mean that they produce work. And the best example I can think of to describe this is if you have an inclined path just here, right? So it's just a standard ramp, right? And let's say you have a box sliding down this ramp just here. So our box is our particle in this case, right? Of course, you're going to have a force due to gravity. And let's say there's a spring here too, pulling it up, right? Well, you're also going to have a normal force just here, right? And you'd be tempted to calculate the work by your normal force, and you should, but I'll save you some time because you wouldn't have to calculate the work done by this normal force because the work will always be equal to 0 in this case. And that's because the normal force is always going to be perpendicular to the direction the block is going to be moving, right? And if you don't believe me, I encourage you to go through the calculus by calculating, your force.dr. I encourage you to prove it using the calculus if you want, but rest assured, you'll prove that the normal force will always produce no work, even though there is another force on this thing. Right? And the whole reason I bring this up is to really tell you that it's possible that if W3, well, in the general case, just W is equal to 0, so no other work is done on this particle between positions 1 and positions 2 other than your force due to gravity and your spring force, then our equation becomes this, where W is equal to 0. And let me copy and paste that. There we go, I just copied and pasted it. It's the formula above, but as you'd imagine, W is equal to 0. That's because no other work was on this particle just here. A pretty simple transition, I'm sure. But the reason I write this down is because this right here is an extremely beautiful equation, right? In this specific case, this is beautiful because this, the sum of kinetic energy plus potential energies, is written as mechanical energy. Mechanical energy, right? It's mechanical energy, once again, is defined to be the sum of kinetic energy plus all potential energies. So your sum of gravitational potential energy and elastic energy, okay? Now, this is the bit where your mind's about to explode, right? What I'm going to say is we've proven the conservation of mechanical energy in this particular case, because if it's true that this term, say, gets really low, maybe V2 slows down for some reason, then it has to be picked up by one or both of these terms, right? Purely by mathematics. If this term gets lower, then these two terms need to get higher. Or if these two terms get lower, then this term needs to get higher, right? Purely from mathematics, you can see this must be the case because this is equal to 0, right? And so what we've essentially proven is that energy just sloshes back and forth between kinetic energy, gravitational potential energy, and elastic energy, which is beautiful. I mean, humans have had an intuitive understanding of the conservation of mechanical energy for thousands of years, but it's only since Newton came along that we managed to prove it formally like this. Okay? And I think that's beautiful, to be honest. I think this is more beautiful than E equals mc squared. But that's just me, because maybe I'm biased and I teach the subject. I don't know. Anyway, guys, that's this video. I just wanted to bring that up. I want to end this video on a minor disclaimer. I haven't talked to you about something called conservative and non-conservative forces. I just want to tease you enough to maybe encourage you to look it up on Wikipedia afterwards if you want. You don't really need it. Just as a quick aside, your force due to gravity is a conservative force. Your force from your spring is a conservative force. But friction, for example, is a non-conservative force. I don't want to dwell on this. I don't think it's very important. But if you want to find out any more about this, just Wikipedia or Google conservative and non-conservative forces. Alright guys, that's it. We've proven the formula. I hope you really enjoyed this series. Cheers.